So now we will go for another system. Okay, so just a minute. Any confusion, anything? Didipriya? Any question or anything? Shall I proceed? Okay, so now come to another question. So this is a question that CCl4, you all know that CCl4 is a gas which has a Becher paper of 213 torr at 40 degrees Celsius and 836 torr at 80 degrees Celsius. Calculate approximate value of enthalpy of vaporization. So you know about this Clausius-Clapeyron equation. So if there is a two state, one is liquid state, let's say what is called yes. So it is this equation basically deals about the equilibrium between this liquid vapor or vapor liquid as well as liquid liquid at different temperature, different pressure, or vapor different temperature, different pressure as well. So this ln is, by the way, so previous result will be 0 for a perfect gas or ideal gas, and for van der Waals gas it will be 1 n square by a square. Now if you take a division between these two gas, this what is called this van der Waals as well as this ideal gas as well as van der Waals, as a result of which you will get the value of 0, which sometimes occurs in CSI and NetGate as well. Now I will go to us and the next question, which is talks about the what is called as Clausius-Clapeyron equation. So which has given two pressure. So if there is a like there is two pressure at two different temperature, like these values, or this is a equation, so where you can get one variable out of given some data on this. So if you do all the calculations, so delta evaporation is coming minus r into ln p1 by p2 by 1 by t1 minus 1 by t2, and this evaporation can be calculated with the help of this equation, where r equal to 8.314 joule per mole per Kelvin, ln 213 by 836 as 1 by 313.15 minus 1 by 353.15. So if you do all the calculation, then you are getting the value of your CCl4 enthalpy of vaporization around 31.585 kilojoule, which is nothing but 31,585 joule. So the answer will be this. Is the answer. So if you recollect, so for first case the answer was this del p del t at constant v, and if you take the ratio for this alpha by beta for ideal gas, it is coming p by t. And coming to next, for this one del u del p at constant t is for perfect gas, and if you take del u del v at constant t for van der Waals gas, that is n square a by v square, that v is the volume and is the effective size parameter, and which basically talks about which basically a correction term for this attraction of the gas molecules, and n is the number of moles. Okay, now if del u del v at constant t for perfect gas divide by del u del v at constant T for van der Waals gas. If it is asked what is the value of this, that will be always 0, because for perfect gas that is 0, for van der Waals gas that is n square by v square, which is not 0. So denominator and one is 0, another is non-zero, so you are basically getting the value of 0. Okay, so this is a ratio for del u del v at constant T for ideal as well as perfect gas, for perfect gas as well as for van der Waals gas. Now you come to a situation where you have been allowed to measure the delta H vaporization. So this is a this is called this Clausius-Clapeyron equation. So there are different forms of Clausius-Clapeyron equation where this delta H, so here it is delta H vaporization, but if you do this, this is vaporization means what? Vaporization means the heat released for to go from liquid to vapor phase, right? Now if you do the reverse, basically from gaseous to liquid phase, that's a reverse vaporization. Okay, for that case the equation will be same, there will be a change in the pressure as well as temperature, change in the pressure. So based on that your delta H will be taken care of. And you do one thing, so you if you see that this vaporization basically is a positive quantity, right? Now if you have been allowed to ask what are the enthalpy of vapor, what is the sign of enthalpy of vaporization from vapor to liquid? Obviously it will be minus. So liquid to vapor is plus, yes, plus, because you need to give the heat to the system so that the molecules will will vaporized. And if you reverse them back, now you have to take the heat from out of this, so heat is negative, it is, so from the system heat is going outside. Okay, and from the for the vaporization heat is going into the system, so as a result of which you are getting the sign positive. Now if you see what is called, yeah, so there is any confusion here for this second and any for these three question 1 2 3? Now if you have been asked, so delta H for liquefaction, okay, for liquefaction, what is this, is positive or negative for liquefaction from vapor to liquid phase? Vapor to liquid, enthalpy positive or negative? Vapor to liquid, so from vapor you are making liquid, yes, liquid, is it enthalpy positive or negative? Anyone? You can write in box also, chat box. Okay, so obviously this enthalpy will be vapor to liquid, obviously enthalpy will be positive or negative? Okay, so Now I will go to the another question, which is nothing but, now I will go to another question. So choose the correct relation between most probable velocity of nitrogen and neon. First you tell me what is the formula for this most probable velocity. For so there are three velocities are available. Okay, three velocities are available. So one is called root mean square velocity, the other is called most probable velocity, the another is called average velocity, right? So out of these three, the most probable velocity is root over root 2 RT by m, and root over 3 RT by m is your RMS velocity. Okay, now for this question, so root over 2 RT by m is the mass of the gas, molar mass of the gas. Now for nitrogen it is coming 14 into 2 28, for neon it is coming 20. Okay, so this 20 20, so these are the mass of the gases. Okay, now if these are the mass of the gases, now if these are the mass of the gases, so for nitrogen it is 28 and for neon it is 20. So if you take the ratio, then it is coming 0.845. So nitrogen, so most probable velocity of nitrogen is nearly 0.8 times of neon most probable velocity. So what is the conclusion from here? The conclusion is that if your gas has more higher mass, then its probable velocity will be less, just opposite, right? So this is one of the conclusion from this slide. Now if you have been if you now okay, now you have been allowed to go to make a comment on this most probable velocity between two isomer. Let's say one is nitrogen 14, another is nitrogen some other isomer, like let's say nitrogen 15, right? So between nitrogen 14 and nitrogen 15, which will be have most probable velocity more? Between nitrogen 14 isotope and nitrogen, just a minute, nitrogen 15 which has higher VMP. Between nitrogen 14 and nitrogen 15, so these are two isotopes which has higher VMP, most probable velocity. Can anyone comment on this? So between these two, just a minute. So as you know, this most probable velocity is inversely proportional to mass. So higher is the mass, lower is the most probable velocity. So between nitrogen 14 and nitrogen 15, so 15 will have higher mass obviously, because isotope mass is more compared to 14. So as a result of which we have lower VMP, most probable velocity. So nitrogen 15 has lower VMP over nitrogen 14. Okay, so this is one of the important thing is that, so higher is the mass, lower is this most probable velocity. Any confusion? Now if you have allowed two things, so this most probable velocity, like higher is the mass, lower is this most probable velocity. Now if you take a situation where you have nitrogen 14, nitrogen 15, nitrogen 16, so nitrogen 16 is not available, right? Nitrogen 14, nitrogen 14, 15, nitrogen 15. So out of three, which will have the higher most probable velocity? Okay, so this is the previous. So now if you see among nitrogen 14, nitrogen 15, as well as just I am giving nitrogen 14, 15, so both the isotopes are there. So which has higher VMP between the among these, like most probable velocity? As I have already mentioned that higher the mass, so you will get lower it is its small most probable velocity. Okay, so between 14 isotope, 14, 15 as well as 15, so nitrogen triple bond is there, so one nitrogen is 14, another nitrogen 14. Now you come to another situation where one nitrogen 14, another nitrogen 15. You come to another situation where both the nitrogen 15. So among these three species, which will have the higher most probable velocity? This is not there in this question, just I am clarifying you or washing your heads. So remember, if there is a, if, so basically you need to consider the concept of reduced mass here. Okay, So nitrogen 14 15, you may consider reduced mass here or may not consider, but if you increase the mass 1 unit, always the mass of the species which has been increased by 1 will have always the higher mass than compared to previous one. So that's why the highest most probable velocity will have, like this nitrogen 14, which is the lower mass, will have higher velocity most probably than the other two. Now you consider another situation where you take carbon monoxide, okay, 12 16. Now you take another carbon monoxide where you will have 12, just a minute, 13 16, which has higher VMP, most probable velocity. Now you consider a situation where you have this carbon monoxide gas, which has carbon has 12 and oxygen has 16, and carbon has 13, oxygen has 16 isotope. So this is the combination where you will get the higher most probable velocity, that you have to understand. So as I have mentioned that this M is for homomolecular system. Now if you go for heteromolecular system like CO, where two heteroatoms are there, in that case you will get the reduced mass. So here the concept of reduced mass will come. So reduced mass is nothing but m1 into m2 by m1 plus m2. So ab by a plus b. Now if b has the value of a plus 1, always a into b plus 1 by a into b plus 1 will have the always higher value than ab by a plus b. You understand? So if there is even one increase of mass unit, for that case you will have the higher reduced mass, as a result of which CO 1316 has lower VMP than that of CO 1216. Okay, you understand? Any confusion or anything else? Now, so is this clear? Now people used to ask one question. So the question is like this. So let's say you have HCl, okay? HCl is gas, hydrogen chloride gas, okay? Now it has HCl 35, that chlorine 35, and you have this HCl 37, okay, which has higher VMP. Which has higher VMP? HCl 35, like chlorine is 35 and 37, two isotopes are there, which has higher VMP. Now I am giving HCl and HCl 35, which has higher VMP. Okay, so these are two questions. So one is chlorine has 35 isotope, 35 like isotope, as well as 37. Now you come to this the below one, HCl 35, which has higher VMP. So can you comment on the below one, HCl 35, which has higher VMP, most probable velocity? Any comment? For ACL is 35, obviously. Am I right? So ACL 35 has lower mass, as a result of which have higher BMP, most probable velocity, whereas ACL 35 both are the same molecular weight and they have the same most probable velocity. So any confusion here or anything else? Any doubt?
Good evening, sir.
Yeah, tell me.
I have a doubt regarding exam, sir. Actually, I am a PhD student, scholar student, so I'm opting for NPTEL courses.
Okay.
So, two of my exams are going to conduct on the same day, that is 26. So, there's a possibility that we can shift that exam date, sir?
Yeah, possibility. You do one thing. You mail. Okay.
Yes, sir.
Did you mail already?
No, no, sir.
No, you mail them and you explain your all the what is called all the your concern. So where do you mail? Do you have any idea?
Uh, uh, on the site, it has mentioned the detail about.
Yeah. Then you can mail. Okay, let me go to the schedule just a minute. I'm just so wrong with recording. Now I am show what is your concern. Your concern was about this. It is written there. PTL. Oh, okay. Where are you going? Where are you showing? What is this course ID? I forget. Advanced.
Advanced Classical Thermodynamic and Kinetics.
Oh no, not that name. This is Professor Orijit something, right? Professor. Yes. What is the exam date? I did not search
Uh,
anything.
it is 26 or 27, sir. 26.
Mm, where the date is mentioned, I do not know actually.
Sir, 26.
26 what? Oh, April.
26
April, right?
April. Yes, sir.
Yeah. So you have the other courses on the same day, right? Exam.
Yes, sir. I have a computational quantum chemistry on the same date.
Okay. So you do one thing, you mail them. Okay. Where is the contact? Did you find the contact
Contact number, sir. On that call, I have contact the coordinator only, sir.
in IIT Madras, right?
Yes, sir.
Yeah, I know. So you contact to. Um, did they reply to your mail?
Uh, I have contact regarding sir elective course only. So they were telling that we can schedule on the same day. You go for morning and then for the evening.
Yeah.
But
Then yeah, but
exam will be conducted on the same day, sir. That will be difficult because both the courses are
okay. Can you tell me the
a
mail
bit
ID?
difficult.
Why did you mail?
Okay, sir.
Now, just on interesting, people used to ask this question also. Mm, let's say you have a CO2 gas, right? So let's say you have a CO2. So CO2, okay, and CO2, this combination 13, 16, which has higher VMP, most royal velocity. So there are two. So CO2, both are CO2, but one CO2 is 12 and 16, another is 13 and 16. So which have higher VMP? Both royal velocity. With increasing the molecular, the velocity will be decreased, right? So can anybody any comment on this? So CO2, 13 isotope and 16 isotope has lower VMP over CO2. So these are all are the deductions is coming from this question. Okay. Any confusion or anything else? Any doubt? out, Santosh? There is
Sir, can you share your number? See, what is happening is what is the question, what is in the textbook, what is in the question. Everything is entirely different actually.
entirely
Actually,
different.
you need an Indian author who can order this book to solve the assignments.
Oh, you need Indian author book, right? You are saying like
Yeah.
this. Okay, I have the PDF of an Indian author. Okay, so I can share that also. That is not a big deal. Okay,
Sir, can you share your mobile number, please?
I am sharing my mail ID. Okay, just to
Oh,
mail me. So you prefer Indian, but yeah, for CSI Netgate Indians are okay, but for other things Indians may not. Okay, I will share you the one PDF. Okay, just to mail reach me to this number. Okay, shall I proceed to our next question? Now you take a concept that is called mm, delta G mixing. Now if you have more than two or three gas, orange gas, if two three gas are separated, when they always try to mix. So what is the reason behind this? The reason is that, sorry, yeah, I will share the book ID. Okay, so this is a book called Physical Chemistry by Puri Sharma Patania. Have you heard the name? Physical Chemistry
no.
of Puri Sharma Patania. So this is in fact a good book which covers all the topics in physical chemistry and which is quite good for CSI and NetGate also.
Can we download this book from someone?
I don't know whether you can download or not, but I have the PDF. I have to search where I have, because I gave CSI NetGate 4 years ago, so I should have the PDF as well. But
So
I
if you,
will. Okay, okay. Let me, as you have said, let me try one thing. Let me search whether PDF is available or not. Okay. Yes, PDF is available. So he is an Indian author. He is probably from Odisha or something like this. So he is a his book is really nice. So it covers all the CSI and NetGate people used to. Let it open. Yeah, this is the PDF. Hello, Shantosh. Hello.
yeah,
This is the
your
PDF.
sense of
This is the PDF. Okay. This is a very good book. Very good in terms of to understand for CSI and NetGate. This is a very every each and every topic is covered here actually.
have you sent? I had sent a mail, sir. Can you just attach that?
Yeah, yeah. I am sending you this what is called this mail. I have this book copy link, right? And you download it and let me know if it works for you better or not. Okay.
Okay,
But you do one thing. You take my mobile number also.
okay.
If anything required. This is my mobile number. Okay, so I did not. Okay. So from where you are? Chennai?
No, Kochi.
Oh, you are from Kochi. Okay. You check whether you can download or not.
Okay, sir.
Okay, so this is so you understand the why this CO2 1316 has lower VMP over CO2. Yes, over CO2. You understand the problem? Okay, hope you understand. So coming to this another problem. So if you always gas will mix each other, because that is the like they always enjoy to mix each other. Okay, which then how you will see these in terms of physical chemistry. So that you can see just calculating this Gibbs free energy as well as mixing of enthalpy. So this delta G mix equal to energy xa ln xa xp ln xp. Okay, so this xa and xp are the mole fractions. So if you calculate, you see that is divided into two compartments of equal size, right? In the left compartment is argon and in the right compartment is was neon. Gives free energy of mixing when the partition, we assume the gas are perfect, right? So gas in both the compartment is has been mixed to each other and which have the same volume, temperature, everything. So just normal thing, PV equal to nRT. So from there you are getting pressure, temperature, volume all are same, as a result of which you are basically getting each mole fraction half. Okay, 0.5, because your volume is only divided by 2. Two volumes are now coming to is half and half. Two volumes is coming to V, means V by 2 plus V by 2. Now delta G mixing is this formula, PV this nRT equal to PV into half ln half plus half ln half. So if you do all the calculation, then you are getting Pascal into meter cube, and each 1 Pascal into meter cube is joule. Okay, so from there you are calculating the delta G mixing. So in this case if you have been given that what is the value for, so what is the value for this delta S mixing. So this delta S mixing is another fake. So this is called entropy of mixing of perfect gases. So xa xb, and these are the mole fractions. So this is the delta S and this is the delta G. So what is the difference between them? Okay, so now to make the process spontaneous, your G has to be negative, right? So this xa is less than 1. Any value below within this log function, ln function will be negative. As a result, we will get this delta G negative. So delta G is negative is spontaneous, right? Now if you consider the delta S concept, so this negative sign is there, and inside that ln or log you will get this less fraction less than 1, so which is negative, and negative both are coming to positive. Okay, so delta S mixing for perfect gas is always positive, greater than 0, whereas delta G mixing is negative. So this is the things you have to understand first, that when two gases or many other gases are mixing each other, then for that case delta S mixing will be always positive and delta G mixing will be always negative, which basically favors the mixing. Okay, Any confusion? Any confusion or anything? So for anything to be mixing, it has to be delta G negative and delta S positive. So these are the two formula from where you can get that how this delta G and delta S basically working each other. So for mixing, delta G will be always negative and delta S will be always positive. And okay, so any confusion here or any doubt or anything else? Any confusion? Okay, now come to the another question. So now look at this system. So this is not in NPTEL class, NPTEL assignment. Now if you take a 4 system, now from 2 I am coming to 4 systems. So helium, xenon, argon, neon and helium, right? So 4 are separated. Now you mix them. Okay, so now you calculate G and S, just these two formula only. Okay, and first you let me know how to calculate this X. Do you know how to calculate this mole fraction? So mole fraction has to be calculated by the, let's say 1 and 2 is the species, where n1 and n2 are the number of moles in the mixture. Now X, say that is the mole fraction equal to Na by Na plus Nb, where Xb equal to Nb by Na plus Nb. So if you take the divided of Xa by Xb, it will be always Na by Nb. Okay, now same way, so this is the system where 4 gases are separated, 1 2 3 4. And now what you have to do is that you have to find this value of delta G and delta S. Okay, so any idea how to find it? idea how to find the value this calculating delta G and delta this one. So this just you can calculate with these two and you will get the value like this. So delta G mix equal to R2 N He by XC, and this one just to get it from here to here you can do by this calculation. So you can get this particular value this delta G. So you can do some little bit homework on this. So if you divide T, so basically R is coming, right? So R into ln x He with negative sign. So negative becomes positive. So as a result you will get the positive. Now, yes, any confusion? Okay, any confusion or anything? Now without delay, so let's go to the another. So now you know the concept of Carnot engine, which is basically depending on the second law of thermodynamics, where this eta is the efficiency of the machine, like 1 minus T2 by T1. Always remember this efficiency cannot be negative as a result of so negative. That means T1 will have higher value than T2. So that's more than enough to do this kind of this kind of question. Okay. Now this is 30% efficiency. This is eta equal to 30 by 100, and the efficiency is to be increased to 50 percentage. Okay. Now you have to find out. You have to find out that sink is 300K, right? So sink is 300K. So T1 will be always higher than T2 because this is the hot source. Obviously, it will have higher temperature compared to this cold sink. Now you get the temperature of this system, right? Now you know the T1, you know the T2. Now you're increased into 50 percentage. Now from there only you have to calculate the value of this T1. So T1 is the temperature of the source be increased if the sink is 300 kV. So this is 600. So previously T1 was 428.57, now it is 600. So you are increasing the source heat, that means you are increasing the Carnot cycle engine, the efficiency of the Carnot cycle. Okay, hence the temperature should be increased by 620 minus 428.57, that is 171.48 Kelvin. Okay, so you understand this problem. So first you have this hot source and followed by hot sink. Now your temperature is coming from hot source to hot sink, and you are basically getting some efficiency. So the what is the efficiency? Efficiency is nothing but to increase the higher number of efficiency, your hot source would be high temperature compared to your cold sink, right? So T2 by T1. So to get it is eta nearly tends to 0. T2 has to be very less compared to T1. So T2 greater than equal to greater than T1. So T1 will has to be high, T2 has to be low. That means hot source have higher temperature than cold sink, as a result of which you are increasing the efficiency of this Carnot engine. Any confusion? now you come to the next question. So the another question will be on Carnot engine problem. So this is very vital from second law of thermodynamics, where so this is the problem. So a steam engine has a boiler that operates at 600 K. The energy from burning fuel, water to steam, and the steam then rises to piston. The cold reservoir temperature is that the outside air, and it is 300 kb. So maximum thermal efficiency. So TH is 100 and TL is 300. So what is the maximum efficiency that you can get? Now this is nothing but the eta, that is the efficiency equal to 1 minus TL by TH. So that only. So if you explain the term, so you have this higher hot source that is 600 and you have lower 300, right? Now your heat is coming from higher temperature towards lower temperature. Now some heat will go to this way, some heat will go to this way. Now analysis of the problem, and okay, node is 1 minus TL by TH. So L is the sink and TH is the hot source. So this is the ratio which talks about the efficiency of this Carnot engine. So that will be always less than 100%. If cannot go beyond 100 percentage. So efficiency of a Carnot engine cannot go beyond 100%. So here in all the cases we will get the efficiency below 100%. So here it is efficiency 5. So 1 minus 300 by 200. So this is the value of half. 1 minus half equal to 0.5. So and this is the 50 percentage. Now coming to the another situation where you take one engine which operates at 1200 Kelvin and 300 kV. What is the efficiency of the engine? So efficiency is 1 minus TL by TH, one minus TL by TH, which is basically 1 minus TL by TH, which is basically the ratio between this lower temperature reservoir as well as this hot sink, and as a result of which you are getting this value. This high temperature is 1200 kV and low temperature is 300 kV. Now you have to calculate the efficiency. Efficiency is nothing but this 1200 minus 300 by 1200, 900 by 1200, that is 0.75. So the efficiency is 75 percentage. So this has the efficiency of the kinetic, the efficiency of this kinetic is 75 percentage. So these are the simple tricks problem that comes in CSI NetGate. Now if you have any query, please let me know. Now combined gas law problem. So we know PV equal to nRT. So from there we have to calculate this. If you give the variable from one parameter, so now we need to calculate the variable from other parameters. So in this case of combined gas law problems, so we will have this. Now this is the first. So if 100 meter cube of atmospheric air is at 0 Fahrenheit temperature are compressed to a volume of 1 feet cube at temperature of 200 degree Fahrenheit, what will be the pressure of the air in psi? So you have been given the volume 100 feet cube feet, and we have the pressure 1 atm, and you have the temperature 1 degree Fahrenheit, and V2 is 150 cube and T2 equal to 200 degree Fahrenheit. Now we have to find out the value of this temperature, this pressure. So any idea how we can calculate this? this is the way you can do. So PV equal to nRT. Now in both the cases your nr is constant, so P1 V1 by T1 equal to P2 V2 by T2. So you know this Fahrenheit, so degree Fahrenheit, so now you have to add to this 460. Now P2 equal to P1 into V1 V2 by into T2 by T1. So this is a PSI. PSI is the unit for this pressure, and just you can from here you can get that P2 is nearly 2109.130 psi. And coming to the, so this is the last question where you have a gas container and you have a gas at 110 kilopascal and 30 degrees Celsius, which fills a flexible container with an initial volume 2 liter. If the temperature is reached to 80 degrees Celsius and the pressure increased to 440 kPa kilopascal, then what is the new volume? So this is also like you have both the NR is fixed. Now P1 by P1 V1 by T1 equal to P2 V2 by T2, and from there you can get this P2 value. So 1110 kilopascal into 2 liter by 303 Kelvin equal to 440 kilopascal into V2 by 353 Kelvin. So 0.52582 L is the volume. So now, so in this way you can do some so these are the very good problem for CSR Netcat, and in this way you can do some what is called, I will say this questions. Now so this is the first session. So now, so this is the first question where we have this calculate this alpha by beta, which is dv del p del t by constant v. Now t is fixed. Now v decrease means p will increase. Now this negative sign basically increase signifies that. So del this is del u del v constant t for this ideal gas or perfect gas, it is going to be 0, and this is for 1 n square by a. Now if you take the ratio for this ideal gas and 100 gas, you are getting that 0, and these are the things. Now you come to the this concept of this most probable velocity, and I have make some question for this, that if there is increase in mass unit or higher mass isotopes, then you will get a lower lower value of most probable velocity. So keeping all the things in mind, now so this is the mole fraction concept, where this delta G mixing you have to calculate, sometime delta S as well, and from there you can now this is the delta S mixing. Now if so, this is the system where this all the four gases are separated by boundary. Now you mix them. Now from there you have to calculate the value of this delta G mixing as well as delta S mixing. So these are the things that is these questions are very important. Now you go to this Carnot efficiency engine, where you can do some concept of this efficiency of the engine, and you can calculate that by just taking the consideration by taking the temperature of this lower reserve lower sink and hot resources. So this is the Carnot engine problem, where I have shown you these two types of problems. So this is a problem, these are the solutions, and this is the another problem, this is the solution. And now combined gas law problem. So this here, if you add 2460, you will get the value of this corresponding same temperature. These are the things. Also take good note of it and go forward. And these are the things: v1 p1 t1, v2 t2, and this is the 2109.11304. Now gas at 110 kilopascal and 330 degrees Celsius fills a flexible container with an initial volume of 202 liter. Now if the temperature is reached to 80 degrees Celsius, now what could be the value of this V2? Now as you know that T1 is 30 degrees Celsius, now you convert it to Kelvin. Same way in this case, from Fahrenheit you have to convert to this Kelvin. Now this is the temperature where you will get this, if you do all the calculation, now you will get the V2 around 0.582 liter. Okay, so these are the questions that will be very helpful for CSI and NetGate as well. So with this I am stopping this today's session. So we'll meet next session on next Tuesday, which will talk about the assignment of second assignment. So thank you very much. If you have any query, please feel free to reach me with my email id cy20d750@iitm.ac.in, and best of luck and do well. So these all are the based on the CSI and NetGate problem, as well as I have taken some assignment from this CSI and NetGate, as well as some assignment problem of NPTEL. So with this I am stopping today. So we will meet on next Thursday and next Tuesday. So that is the date of so next Tuesday is, sorry, 4th February. We will meet on 4th February. So with this I am concluding today's session, and we will do in the next session. Thank you very much.